Okay, in example 8, we're going to practice writing expressions of K and Kp, giving us an opportunity to practice the difference between the two and what they look like. But we will go back to a little bit of a first year, blend it with a second year skill where we're going to have to write a balanced equation first. So as this is described, you won't be given the equation, you'll expect it to write it. It says the reduction of black solid copper 2 oxide, that's this, plus hydrogen we assume to be a gas unless we're told otherwise, and it's diatomic, equals copper metal solid plus steam, which would be water. So here is my equation. I want to balance this. It's 1 copper, 1 oxygen, 1 oxygen, 2 hydrogens, 2 hydrogens, so it's balanced. So we write it, balance it, then see if it's set to the way it's requested or asked about in the problem. We need 1 mole of copper oxide, that's what we have. And so now we're going to write expressions for it. If we were asked to write equilibrium, a K expression, using concentrations, how do I know to use concentrations? Because there's no subscript with this, so I assume K, equilibrium, if it asks for just K, that's equilibrium expression, then I know that it's going to have concentrations. So I will put H2O in square brackets, and I do not include copper solid, because remember, we do not include solids or liquids in our expressions, and therefore the bottom part, or the reactant side, would be hydrogen gas. We don't put in copper 2 oxide because it's a solid state. So this is the K expression. The Kp expression would look very similar, except instead of square brackets, we would use pressure of H2O over the pressure of H2. And again, remember, I'm leaving out this one because it's a solid, and carbon oxide because it's a solid. Okay, moving on to part B, 8b, a reaction of 1 mole of steam with red hot carbon to form a mixture of hydrogen and carbon monoxide called, and so and means plus, called water gas. So these two together in a beaker are called, or in a vessel are called water gas. Now we need to make sure it's balanced. So we wrote in balance, 1 carbon, 2 hydrogens, and oxygen. So we're going to write the K expressions. Both of these would be included, and water would be, but not carbon because it's a solid. That's the K expression. Square brackets means moles over liters. The Kp expression would be to plug in pressure values. Okay, for 8c, now we're given an equation, so a little bit different on 8c here. We're given an equation where it says the Kp for the reaction, so the Kp for this reaction is at 450 degrees Celsius is 27.3. So our Kp value, a lot of stuff in the way, but if you read this the way it's read, you will see that this is the equation, this is the temperature, and this is the value that they're talking about Kp to be. This is our R constant from the previous value, from the previous slide. This is the ideal gas law constant in atmospheres. Notice it has liter atmospheres over mole Kelvin, but you can have different R constants depending on what value of pressure. We are going to use the atmospheric R value, or the gas law constant, with respect to atmospheres. Okay, and you'll be given that, so you don't need to memorize that. It says calculate Kp for the reaction of 2 moles of gaseous hydrogen chloride with oxygen to form chlorine and steam. So we got to ask ourselves, forward or reverse? We know Kp is 27.3. We're looking for Kp then when it is 2 moles. So we have 27.3 is when we have how many moles of hydrogen chloride? Well, here's hydrogen chloride. We know it's 27.3 when it's 4. So this is similar to what we've done in the past. I need to ask myself forward or reverse. Well, I want to see hydrogen chloride reacting, so it's going to keep it forward because this shows hydrogen chloride reacting. But I want 2 moles. I want to know Kp for 2 moles, so I'm going to keep it forward and multiply by 1/2. Remember that if we keep it forward, we keep it as it is. And if it was inversed or reversed, if we would have reversed our reaction, we would have taken the reciprocal, or 1 over K, I should say, or K would have been under 1. So because we kept it forward, though, we would not do that. And it's to the times 1/2. To get 4 down to 2, we have to multiply by 1/2. So we're going to raise our Kp value just like we would have raised our K value to the 1/2. And that's how we get this value here. Now, the beginning of this problem asks for K and Kp. So I'm going to also show you how to get from Kp, which we have, to Kp. Excuse me, from Kp, which we have, to K. Let me try that again. We have Kp, we want to get to K. We're going to use this relationship that we talked about here to do that. Okay, so we're going to plug in our Kp of 522. That goes where Kp is. We're looking for K. We know this is our given ideal gas law constant. We're going to take 450 and convert it into Kelvin by adding 273 to it. So if I would take 450 plus 273.16, I get this 723.16 or 723 with sig figs Kelvin. So all of this is just plugging it in, and then my delta N is going to be the sum of my products minus the sum of the reactants. And I can only use the things that I would have in the expression. So again, I would ignore solids and liquids, solids and liquids. So I see here that I have 2 moles of this gas and 2 moles of this gas. So on the product side, I have 4 moles. On the reactant side, I have 4 moles of gas here and 1 mole of gas here. So I have 5 moles. So I'm going to take 4 minus 5 because I'm going to take the product side minus the reactant side. So 4 minus 5 is a -1. So I multiplied these two numbers, ideal gas law constant and my temperature, and I got 5.93 times 10 to the first. Now I'm going to raise that to the change in N value, which we just talked about as -1. I get this value, 1.69 to the -2, and then to get K by itself, I divide both sides by 1.69 times 10 to the -2. So make sure that on this problem you've done both things. You've solved for Kp based on what is described here in the question mark, in the question prompt, pardon me, and then just to practice using this relationship, also take yourself through solving for K and getting this answer. Okay, here is another example where we're going to solve for K and Kp for the reduction and go through this. Let's go through this together. So let's calculate K and Kp. So we know K for this reaction is this. Now remember, sometimes the problem with these word problems is you have to be careful about what you're reading. So as you read this, it says K for the reaction of this at 1,000 degrees Celsius this. So this is my K value at this reaction set to these coefficients at 1,000 degrees Celsius. Now we're going to calculate K and Kp for the reaction of the decomposition. That's a horrible sentence. Let's try that again. It should say, for the decomposition of COF2 to 3 moles of carbon dioxide and 3 moles of carbon tetrafluoride. So I want to decompose this to form 3 moles of carbon dioxide and 3 moles of carbon tetrachloride. So right now I have 1 mole of each of these, right? So I need to think about 4 to reverse. What do I multiply by? So we have to reverse it because this does not show carbon COF2 decomposing. It shows COF2 being formed. So first I have to decompose it. I have to reverse it. That's what I did here. And I need 3 of each of these, right? I need 3 moles of each of those, so I have to multiply through by 3. So I take my K value, which is 0.5, and because I reversed it, I put it underneath 1. And because I had to multiply by 3 to get what it asked for in this problem, I raise it to a 3. I get an 8. So that's my K value. Why K? Because I was given K to start from this basic equation. If this would have been Kp, then this 8 would have been Kp. But because I was given K as 0.5, I'm going to use it and then now solve for Kp. So now I'm going to plug in my K here as an 8. This was my K. This is my ideal gas law constant. This is my temperature converted to Kelvin. And let's look at the moles that we have. Now we need to be careful about this because remember that when we look at this, we have 2 on this side and 2 on this side, but technically, when we did all this work, we reversed it. So it would have been 2 minus 2, right? But it would have been how I would have written it in the reverse position. So 2 minus 2 here is 0, so anything raised to the 0 power is a 1. So that's why my K and my Kp are 8. Because when I take 2 minus 2, right, there's 2 moles here. This would have been my, if I'm decomposing it, this would have been, these are my products. So there would have been 2 here minus this 2, which is 0. Because remember, this would have been reversed, so this would have been 2. And this first 2 comes from these 2 would have been my products, because I had to reverse it. And this was my other 2, my reactant. 2 minus 2 is 0. Anything to the 0 power, so this whole piece of parentheses raised to the 0 power, anything to the 0 power is 1. So K and Kp would be the same value.